So welcome to Silent Data Corruption, Specification Overview, and Metrics. I'm Rob, and I'm here with Lidia and Vilas, and we're representing the Server Component Resilience workstream, which is underneath the Hardware Management project. So the context of our talk is silent data corruption and how it's emerged as a very difficult challenge in data centers. And if you've been to OCP in the last few years, you may have seen one of our talks or our panel discussions about this. If you want more information on those, I've got links in the call to action slides, so you can follow up on those. But if you have or you haven't been to one of the previous things, silent data corruption has emerged as a difficult challenge. The reasons are, very briefly, it's hard to diagnose as a hardware problem. It's possible, but it usually takes months of work before we can conclude that, which is not scalable. It's virtually impossible for a data center operator to even know how often a silent data corruption event happens. The S stands for silent, so kind of by definition it's difficult. We can find defective parts, but knowing how often it happens is also challenging. And the way to solve this in other forms of computing is typically through redundancy, and we can't really do that at cloud scale. You can imagine that it's hard to even provide enough capacity for all the demand today. If we had to double or triple it for redundancy purposes, it just doesn't work. So the way that we've been dealing with this as an industry is through testing. So we're screening, writing specialized tests to find defective parts so that we can remove them from our fleet. But we can always do that better. And to do that better, we want to engage more of the industry and more of our academic colleagues to try to produce better testing. Not only does the testing have to be effective and that it can find defects, it also has to be efficient. This is because we're taking time away from the actual usage of the server in order to try to do testing, which is costing capacity, it's costing power, it's costing time. And so we obviously want to minimize that as much as we can. And to the extent that we can find defective parts, it actually creates a virtual feedback into designs, because now silicon providers can learn from all of that information of what kinds of defects are manifesting in the field and then design so that they don't occur in the future. So for the purposes of trying to build better tests, we formed the OCP Server Component Resilience workstream. The 7 companies here are represented, and we're happy to be talking about our first specification release. So you might be wondering, how can a specification help design tests for SDC detection? Well, first of all, SDC testing is challenging. Even though it's a problem for us, it's a problem because of the extreme scale. So trying to do experimentation with tests also requires extreme scale. Not only that, if you want to find what's wrong, you need intimate design knowledge to make sure you're testing all the subcomponents. You need knowledge of silicon fault causes so that you can try to hit the right conditions. And it's really a multidisciplinary distributed problem. And so what the specification is doing is it's giving a common language so that we can discuss the problem, we can experiment, and we can do analysis on the solutions, and we can eventually move in a direction of better testing. So what's in scope in our specification is components, the major components that do computation, such as CPUs, GPUs, and other types of accelerators. We cover terminology so that we can be speaking the same language. We cover information exchange formats. This is to facilitate experimentation. And what we'll be presenting today is metrics for the first time, which is how we determine quantitatively whether a test is better or worse than the existing. What the specification is not is the procedure to go and access experimental machine pools. That's outside of the scope of the specification for OCP, and it will be a case-by-case basis for the provider. This is what the table of contents looks like for the specification, and the contributors are recognized over on the right. The meat of it is sections 5 through 10, which are talking about the definitions, the information exchange formats, and in the future version, in the 0.5 version, the metrics will also be included. So the first thing that we did as a work stream took surprisingly long, and that was to agree on the definition of what a silent data corruption causing computing system is. And this is because that term is used in many different circles in the industry, and it kind of means different things to different people. So we're trying to produce the cloud-relevant version of that for server nodes in the cloud. And this is what we settled on. A faulty machine is categorized as SDC-causing if we can identify a bug-free workload which can either be a test that's created to do a screen, or it can be an actual production workload. And it produces incorrect results without any indication from the built-in error detection mechanisms. So that's what we call an SDC-causing system, and the tests that we're writing are aimed at finding those things so that we can take a repair action. So I'm going to hand it over to Vilas now, and he's going to talk about information sharing and the methodology.
Yeah, thank you, Rob. And so I'm Vilas Sridharan from AMD. And I guess before I talk to the slide, let me just echo what Rob said, right? This is it's a very hard problem to talk about because by definition these are silent. And so, it's even coming up with terminology took a really long time. But we think this is important because we want to be able to harness, as Rob said, like academics, the entire industry to help solve this problem. And so what we will need to be able to do is talk together using a common language, using a common framework, right? And so that's what we're starting with here, with the information sharing, right? And so the goal of the information sharing portion of the specification is to standardize information exchange to enable collaboration, right, across academia, silicon vendors, and the wider industry, right? The cloud service providers, everybody with a stake in this problem. And so ultimately, this will accelerate early detection of detective chips, right? And early doesn't just mean in the fleet. Early could mean before they get to the fleet in some way, shape, or form, right? So the earlier, the better. And so this information sharing, it can create the communication pathways and transparencies to accelerate the work. And it can, as Rob alluded to, enable a broader community to run experiments on defective machines, right? Because today, as an example, the people who get to write tests on a given node typically are either the cloud service provider or the silicon vendor, right? And that's a limited number of people, and it's far and away not all of the experts in the industry or in academia in the community, right? And so really the goal is to harness the broader expertise to help allow more experimentation, better testing, right? Now, this is hard, so we're taking a staged approach, right? A crawl, walk, run approach. The crawl stage, which is, I think, roughly where we're at right now, is really just providing data, right? It's establishing a baseline, right? Providing data on defective chip characteristics so that we can better understand failure modes. And I think one of the main things I'll mention, right, is a silent data corruption is a symptom of an underlying fault. The faults may or may not all be the same faults, and what you really have to do in order to write better tests, in order to really understand what's going on, you have to reason about the faults. So starting out with data and the ability to understand what the root cause of the SDC is really fundamental to going and solving this problem, right? So that's part of the crawl stage. And then as part of that, it's okay, establishing a process to track all of that data and all of those contributions and so on, right? So really the first step here is understanding the problem or problems that exist. The walk stage is building on that. It's establishing test development frameworks for creating new testing solutions, right? So there's a bunch of, I will call it, anytime you want to run a test on a machine, there's a bunch of logistical work that has to be done just to get your actual test up and running on that machine. And the more we can standardize and have common frameworks to automate that logistical stuff, the easier it is, the quicker it is, and the more effective it is to get tests up and running, right? And so that is the really part of the walk phase, right? Is take some of the common stuff and create standardized ways of doing it. And then as part of that, also provide guidance for the development of new tests, right? So this is all sort of establishing the common stuff and making it so that it's easy for someone to actually focus on making the test better, not on, hey, I need to get the test to run over here, and how do I do that? And then the run phase, the last phase, is establishing a process and a method to evaluate new solutions on faulty and suspect systems, right? So this is really where we are iterating on the tests and getting better tests and running new techniques and doing research and enabling others to do research and fundamentally, ideally, inventing new ways of solving this problem, right? And so that's really where we want to get to, but we need to get there in a staged way. So going back to the crawl phase, the information sharing, the data content. So we want to start by establishing a library of systems with defective SDC-causing. This says CPUs. It should really say CPUs, GPUs, and other accelerators. Sharing key fields. So this, sounds simple, but it's really, hey, here is a defective part. Here is a bunch of information about this part that might be interesting to understand the defect better, right? And that helps everybody start to get a better understanding and develop better techniques and be able to target their tests, right? And so there's a number of different fields that we've put into the initial information sharing framework. Device type and device architecture, whether it's a CPU or GPU, what's the ISA, what's the technology node or nodes that part was manufactured on, what tests were applied during manufacturing, and so on, right? So I'm not going to read through all of this, but I will just say that the collection of people from all of the companies that Rob mentioned working on this problem have sort of agreed that this is a good baseline set of information it's a necessary set of information that people need to know in order to reason about a defective part. Okay. And so this is just some examples. I am not going to read this eye chart to you, but this is, you can go look at the 0.3 version of the spec to see this is just an example of that in practice with two, what I understand are real defective chips that have now been, sort of logged in this framework. Okay. And you can see all the different information logged about each of these chips. Okay. So that is the information sharing kind of in a nutshell. I'm now going to turn it over to Lidia to talk about the new part of this, which is metrics. How do we know what a test is good or not?
Thank you, Vilas. I am Lidia from nVidia, and I'm going to talk about the metrics that we're going to use to define or to determine how good a certain screening test is. And first, before we actually go into the metric, we want to understand why is a test better than another. A test can be better because it finds new defects, unique defects that other tests have not found. Or it could be better because it finds more defects than another test, so it has a better test coverage. It could be better because it reproduces errors faster or on more systems or more errors. So it has better reproducibility. Also, detecting the errors faster is an attribute that is important for a test. And last but not least, the cost associated with testing is important. So the cost in this case is the number of resources that are needed to perform that test in the data center at runtime. So these are resources that would not be used otherwise for productive work for certain periods of time. As probably all of you intuitively know, a test is more than just the binary, which is going to be provided by the researcher or by the silicon vendor or by the CSP. A test is a tuple that includes the test time, and the hyperscaler is going to determine what test times are manageable in the data center, and as well as the pool version, the hardware that we're testing on. And again, this is something that the hyperscalers are going to maintain. Also, part of the test tuple, we have to have a framework which is used to run the tests consistently, because otherwise, tests may erroneously look better than the others. Also, before we go into the metrics, I want to give a few more definitions to help understanding what we're doing. The tests are going to be performed in a hardware test pool, which is a representative set of hardware that includes servers with CPU, GPUs, FPGAs, accelerators with known and suspect defects. Because a pool is very general, and we talked about multiple types of hardware, And we could also have multiple skews and multiple types of defects that only affect a certain type of hardware. We're going to have the ability to divide this pool into multiple test subpools, such that a test can be measured against that particular subpool. Also, to be able to have threshold or something that we measure the test against, we're going to create a test suite baseline. And in this case, at a certain point in time, we're going to have a known set of tests that expose silent data causing defects at a known rate, and they're going to represent the baseline. But as we all know, hardware evolves. We're going to get new SKUs, we're going to get new microcode, new firmware, new defects are going to be discovered. So to take that into account, we're going to create a periodic pool snapshot to be able to cover these changes. And here is our metric. Our metric is the test efficiency, defined as 1 over time to failure measured in hours. The test efficiency has an additive property. So as we discussed on the previous slide, we can have multiple subpools that it applies on. So the total pool test efficiency would be a sum of the test efficiency on different subpools. Also, if a test does not find a defect, then its test efficiency is going to be 0 and its time to failure is going to be infinite. In many cases, a defect is found through a timeout. So in the case the defect is found through a timeout, then the timeout duration is actually going to be time to fail. And here, just for a little bit of a better understanding, we're giving a couple of examples. In this case, we're looking at 2 tests, A and B, that run on the same pool of machines and that have different times to fail. And you can see that as we calculate the test efficiency and we calculate the total test efficiency, test A seems to be the test that is less efficient. Test B is highly efficient, but it is highly efficient because it detects one of defects very fast. So you may say, well, maybe I wouldn't choose that test because it's only efficient for test X. And that is something that can happen. The metric is flexible. It gives the user the capability to choose how to apply it. So if someone is interested in finding defect X very fast, then they're going to use test B. If not, then they can apply additional weight factors, or they can choose based on the total test time. For example, for test A, it's 5 hours to find both defects X and Y. So I mentioned weights. This is a case where we can add weights for to take into account a certain defect that is only found by one of the tests, that is defect Z, which is found by test A, and it has an infinite time to failure for test B. In this case, if we do not apply any kinds of weights, then test A seems to be less efficient than test B. But if we really care about finding defect Z, because maybe defect Z is something that causes more havoc in the data center through through downtime or recovery from checkpoints, etc., then we can apply a certain weight for defect Z, and now test B that uncovers it, test A that uncovers it becomes more efficient. And I'm going to pass the microphone to Rob for the summary.
Thank you, Lidia and Vilas. So just to recap what we've talked about today, silent data corruption is a difficult problem in data centers, and we've come together and formed a work stream to try to address it. We've published our first version of specification, which is 0.3, and it provides a terminology and information exchange in order to facilitate discussion and experimentation. The 0.5 version is the first one that will cover metrics, which Lidia just introduced, and that's the way to quantitatively capture goodness from a test binary run for a specified amount of time on a particular pool version. If you're interested in this problem and want to come and help, the specification 0.3 is now available, and 0.5 will be ready before the end of the year. You can provide feedback through our email address, or now that our specification is released, we're going to schedule office hours for discussion. And if you'd like to know more about this interesting topic, there are all of the links to the previous OCP presentations and panels, and several of those have links within them that link to other forums and publications for even more information. Okay, I think we have 8 minutes for Q&A. Yeah, please go to the mic if you can.
Hi, I'm John Mine with Tartan Silicon. We're developing an IP that can help weed out these failures as well as monitor the chip throughout its life. One thing you haven't addressed is what's causing these failures.
You want to take that one, Vilas?
Any idea?
Yes.
Yes. This is not a new problem in the industry. I think that the recent thing is the realization that it manifests at extreme scale. So the difference now is scale. But the underlying causes, I don't think, are news to anybody.
Yeah, and I'll add, right, I was giving a facetious answer to your question. One of the differences is scale. The second is the complexity of individual devices. And, you know, I'll just say it this way. It is the same way that Rob said that it is, I'll say, economically infeasible for a cloud service provider to run every workload twice or 3 times. It is economically infeasible to exhaustively test a given piece of silicon, right? For any silicon vendor, that's a general statement. And so that's a true statement. So that's really the set of problems that we're dealing with.
So eventually, every chip fails or wears out.
So yes.
I understand in
yes.
physics, and
so,
it gets worse at the smaller geometries.
Right. So that's why it's important to reason about the root causes, right? Aging, the variety of different aging effects is one of the potential root causes. I'll go out on a limb and say that's not the primary thing we're dealing with at this point.
Yeah. Huh. Thank you.
Yep, over here.
Hi, I'm Meeta Sagi from Pure Storage. I may have missed this on your slide, but on the slide where you had the kind of information that you collect on each failure, is there an environmental component to that? For example, do you also collect information like, did this failure happen, or did it happen at a very low temperature or specific humidity? Because having debugged some of these silent failures, I've at least seen relationship to one specific one where the transmit buffer of a SoC NIC was corrupting data. That only happened when the fans were turned down lower. That means it was happening at a low temperature. At regular temperature, it just wasn't happening.
Yep, totally agree. And I'm looking here to see if we actually put it on the slide, but it absolutely is something that we collect and put into models in order to project. And so I don't know if there's anything on here other than additional diagnosis details that would capture that. But
And I think this is still, the spec is still evolving, the information is still evolving. I believe one of the things we're talking about is splitting up the information into multiple pieces, because there's some information that is important, and that's mostly what I talked about like fundamentals of the device, of the silicon. There's a second set of information, exactly like what you said, is what's the test environment, what's the temperature, what is the runtime environment when this happened, right? And I'll just say it's not always possible to have all of that information all in the same place. And so I think, this is evolving, but definitely we'll make sure that that kind of thing is included in that.
Temperature is especially difficult because what you actually care about is the temperature in the locale of the defect. And so if the entire thing is hot because the fan broke, well, yeah, and then that part's going to be hot too. But the temperature gradients within the die itself can be highly variable. So you would need a measurement that's close enough to be relevant. And that could be challenging depending on how many temperature sensors exist.
Thank you.
Hi, thanks for the great talk. The question I had was, how much of this, the process node dependence, how does that play with the standardization, right? Because the failure modes which you uncover, which are previously silent, a lot of those are going to be die with a particular technology node or particular IP. So how does the information exchange part work there in terms of making this a more global kind of a solution? Yeah.
Well, that has to be in the set of data for the reasons why you suggested it. Were you looking for more than that, and that, like, other than detecting correlations to particular process nodes?
I mean, maybe I can answer a little more, right? I mean, you're absolutely correct that different process technologies are likely to have a different set of fault modes occurring at different rates, right? That is absolutely true, and that is something that we need to grapple with. Now, I think the main thing I'll say, right, is the things that we believe have changed that make this a hard problem, the scale and complexity, are actually somewhat process node agnostic, right? So that is sort of knowing what the technology is and knowing what the fault modes are for that technology is a critical set of information to go into this effort, but it's sort of input into the effort, if that makes sense, right? It's not like, I don't know, it's not the answer, right? if that makes sense.
And I also wanted to add, this is why we are creating subpools based on different types of SKUs, different types of technologies, even microcode and types of defects, because that allows us to separate and to understand the defects better. We don't try to address them as something that is globally valid, because we understand it is not.
Any further questions?
I'm curious, when you're generating this pool of defective processors of various types, how are you isolating the defect to that unit instead of maybe a transient memory fail or other ASICs on the board or anything like that, since these can be really rare and difficult to reproduce? Do you have any procedures around that?
There are two types of machines that we intend. Just lose it? Oh, there it goes. Two types of machines. So there's the set that have been overcome or have been already detected as defective by an existing test. So that's we've run a production screen, we found a machine, and we're going to isolate it. We often call those quarantine pools, where we're taking it out of the general population. There are other nodes where we don't have a test that hits it, but it is behaving in a way that suggests something is wrong with it. And so at some point, we kind of give up on it, and we take it out of circulation, and we can stick that into the same pool. And so then you have the possibility of writing a better test that finds an existing defective node just faster, better, or you can maybe get a confirmation on one of those suspect machines that it's bad. Mm-hmm. And so that's how we make those available.
And I will speak for Rob and the other hyperscalers when I say they've spent a lot of time and effort figuring out how to isolate an SDC to a given component.
Yeah.
It's not easy.
Yeah, no. The ability to test does not eliminate the need to do the root cause analysis and failure isolation. That continues to be a very important skill.
Like I hinted at earlier, the skill of doing that does not scale very well with the cloud. So we can't spend 6 months debugging every SDC.
Yeah, so
Hi, this is Tomer from Synopsys. Can you elaborate more about the failure mechanisms? You mentioned that aging is probably not the biggest thing you're dealing with. So what is?
Yeah, this is Vilas's favorite subject.
I'm going to answer the first question and just say no. Yeah, so this is part of what makes this hard, right? To give you a more detailed answer, it actually depends, right? So I'll just say it this way, you've seen AMD on the stage, NVIDIA's on the stage, Intel has been on, various presentations, Google has been up here talking about their devices. There's not, as best as we can tell, one thing that's right. If there was one thing, we'd have figured it out and fixed it, right? This is, I'll just say, a pervasive set of problems, a pervasive set of fault modes that are occurring across silicon in higher rates than before because of the complexity and the scale. So there's lots of individual things. Most of them are not new in the sense of, kind of research new, but finding them is challenge, right?
And I guess if I had to put it into groups that aren't aging, I would say test escapes are one, where it makes it to production just because we didn't hit it, bad luck or lack of coverage from the tests run at manufacturing and system integration time. So that's one class. And then another class is early life failures, where you have something usually within the first 6 months or a year of production operation where you have a defect manifest, but it's not the same fault modes as an aging case.
And I can actually give you an example because AMD's talked about this publicly, right? If you think about a small delay defect, that's a defect that causes a slight slowdown in a specific path at a specific temperature, voltage, frequency, and data pattern, right? And now testing every path in every chip at every temperature, voltage, frequency, and data pattern is an intractable problem, right? So that's an example, but that kind of gives you an idea, right?
And so if that comes through as a test escape, but it's like a systematic problem, then once it's found through failure analysis, then you're going to plug that hole. But from a CSP perspective, we might have 100,000 parts that don't have that testing. And so then we have to go plug it up on our side with a test also. Okay, we're over time, so we got to
We're good, but I just want to note that you have not ruled out aliens.
No.
Give him a hand. That was a good talk. Thank you.